Today I'm going to be presenting a tale of scaling up in the streaming platform. So, first I'm going to start by explaining the Revolut architecture at a 10,000 picture. Then I will explain what is Event Store, the system that I'm going to be presenting. I will briefly cover the features, and then we will basically spend some time getting into the inner workings, and then basically explain some stories about how we basically scale this platform. And finally, of course, we're going to have some time for some Q&A, and then in case there is more questions, I will be in the Revolut booth, and I will be happy to talk with any of you. So the architecture of Revolut, I would say has a scale as the typical, scale-up company. So it started back in 2015. It started like many companies, as a monolith. This particular monolith was kind of like an anti-pattern. So it was, one monorepo, but reading and writing from the same database with all the problems that was causing. Gradually, they started to move towards a distributed architecture. So around 2019 is the moment that I joined Revolut, and around there was this big effort to basically move away from this monorepo, this monolith, and moving towards distributed architecture. And then the last push that has happened last year is we have started sharding our components, because historically, Revolut has been operating from a single data center in Google Cloud in London, and because of a mix of scalability issues and regulatory concerns, we needed to basically start distributing Revolut across the world. So basically, that has been kind of the last push that we have been getting. So. Next, I'm going to explain briefly about Alpha, which is basically our domain-driven design framework that helps us to basically implement our CQRS architecture. So, on the one hand, this framework allows you to build models. So models are, from a DDD perspective, they are entities, but with some specific characteristic, which is they are built around state machine. Whenever the state machine basically transitions states or perform mutations, we issue models. These models basically basically describes the different state change between those states. On the other hand, we have actions, and actions you can think of as similar to functions. They accept some parameters, and these parameters produce some output, where this output are the model mutations, which eventually will produce the events that I was mentioning before. Also, one characteristic about these actions is the actions are kind of small units of business logic. So, is create an individual, or log an individual, or change the name of an individual. So basically, there is specific actions. So if you think in the typical, service where you have a bunch of operations that you can execute, an action here will represent one of these single entities. And then one distinction here is whenever you execute the action, we produce models. So the idea is whenever you produce the action, you create a model event, action event. This action event has information, metadata about the action execution. So for example, which parameters was getting, what was the outcome of the execution, and within it, we have information about these model events, which is basically where we're going to be working later in the talk. So now we have this framework that produces all these events, but basically you need to do something with it. So that's why we introduced, in the early days, this Event Store system. So Event Store is our audit log, business audit log. And in addition, we have all these streaming capabilities to basically be able to stream events across the Revolut platform. So we build it totally in-house, so we don't leverage any of the solution. And right now we have data since 2016. Revolut started in 2015. This Event Store system, for what I heard, was alive even in 2015, but basically the streaming side of things was existing before the audit log, instead of being the other way around. So, in terms of technologies, we use the typical Revolut tech stack, which is we use Java for the business logic, we use Postgres for the relational database mapper, and finally we use some Redis for distributed logging and some key value. So especially Java and Postgres is basically the battle horse for Revolut for most of the backend components. So, in terms of which functionality supports Event Store, so we have the audit-log. So we'll explain briefly, in case people are not familiar. So the idea is, as I was mentioning, whenever there is a mutation, something happening in Revolut, we represent it as events, and these events are basically recorded, stored into this central component called Event Store. These events, basically, you can use them for a few things, no? So you can use them, for example, for for troubleshooting. Okay, sorry. You can use them for troubleshooting. So whenever there is you're investigating an issue, whatever, you're able to basically see the whole life cycle of one of these models, where a model can be a transaction, a pocket, a user, whatever you're modeling at the time. And also, we are using intensively for regulatory and internal audits. From time to time, we have regulatory audits because of where basically they came and they request us to basically verify what happened in Revolut at a given point. And basically, through those events, we're able to basically give them all this information. And then also useful for developers. When you're building a feature, you're able to basically snip quick what happened at any point, and basically you can do, you can change your systems and create them in an appropriate way. The other hand is, I would say, more straightforward, which is the event streaming side of things. So, it allows to, service to subscribe to service, and basically this enables to have a loosely coupled architecture instead of basically, having intertwined connection between services. So, at least in Revolut, we are using it to invoke callbacks. For example, example that I'm showing there, you get a transaction completed event, you basically tap with your phone, and then as a side effect, we send an email, send a push notification to your phone indicating that the notification has went down. But also, we calculate FS risk, we calculate fee grind risk, we can update some spending projections somewhere in the system, which is also, we use them for distributed workflows. So, you can think of Saga pattern and stuff like that. So all of this is basically driven through events that are also flowing through this system. And finally, to build data projections, as I was mentioning. So instead of executing, service A, executing expensive operations over another service, they are able to basically create a materialized view locally, and then basically they can go as hard as possible, where the events are basically fed through event stream. So, in terms of numbers, I will go quickly. So, we have persisted historically around 500 billion events. That means we are storing right now around 1 petabyte of storage. And then in terms of applications, we have 374 applications that publish events to Event Store, and we have around 400 applications that stream events from it. And in total, this system is basically backed by 21 shards, and then we have 12 archive DBs where we keep historical data. And then, to put something more manageable, in the last week we have persisted around 6 billion records, and we have streamed 71.3 billion events. So, how does it work under the hood? So, first, we have on the left the publisher application. The publisher application is any application that is executing this alpha framework. Whenever an action is executed, it produces the events, and these events eventually will sent to Event Store that we have on the top, where it will be persisted into what we call, in a simplistic way here, DB events, which is basically our clusters of Postgres databases. On the other hand, we have on the bottom the consumer application, and a consumer application is any application that stream events. So they're able to provide, certain queries about the events that are meant to be receiving, and they will create the streams against the event stream, which basically connects with DB events in order to retrieve the data from it, and then we have Redis for key value storage. So we will go a bit more in detail in a sec. So first, we start with how do we publish those events. So for that, we are implementing the transactional output pattern. This is basically, I would say, quite straightforward. So the idea is, whenever, for every model, we have a dedicated table. So for example, you have a identity model, you will have an identity table. So as part of this transaction, we persist the events and we persist the action mutations. With that, we ensure that events and mutations are persisted in an atomic way. Then we initiate a asynchronous publishing towards event store as a best effort. But of course, this publishing can fail. For example, let's say in the middle of the publishing of these events, the DB can crash. Sorry, the service can crash. There can be a rolling update, whatever. So for that case, we have a process that is periodically checking the event log, and whenever it detects that one event is not acknowledged by event store, it will keep repeating it. So basically, this reconciler will act as a infinite loop in a way that ensures that every single event that gets persisted into event store, it gets eventually stored into event store system. And then, well, the step 3 that I just skipped, whenever we get acknowledgement from the event store that the event is persisted, we will go back and we will mark it, because this event log, apart from having the actual event serialized, we also have some Boolean column that indicates whether the event is acknowledged or not. And based on that, we will keep retrying. Then on the other hand is, once this event is persisted, how do we stream this event? So for this case, we have basically the processor and we have the event stream. So the processor initiates basically a channel with the server side, where we have basically 2 streams, one outbound stream and one inbound stream. The outbound stream will publish commands and queries to the server side, and then as part of the inbound stream, we receive the events that are being streamed, that are being persisted or historically persisted. No? So we decided to use for that reactive stream. So for that, we, since this service is Java, we're using Project Reactor. And in order to basically bridge the gap between the client code and the server code, we use one technology called RSocket. And RSocket basically helps us to create a stream from the client component and basically stream it all the way to the server side. So from implementation perspective, we're just dealing with a string. We don't need to deal with any network interactions. Basically, this RSocket helps us with that. And then every single metadata, for example, where store information about the offsets, store information about the events, and so on, we persist it in Redis. So Redis, we use it as a small key value store. And regarding streaming, what we do is basically we have 2 streams in reality. So we have the offline string. The offline string retrieve historical data. And we have the live string, which helps us to keep events, the real-time events. So whenever you persist the event, this event appears right away. So what we do is we initiate a offline string, and then we concatenate it with one of these live strings. So basically, you get the illusion that you start streaming from, for example, 5 minutes from now. You will continue streaming for those 5 minutes, and then you will continue streaming with every single real-time event that you get stored. So for the blind string, basically I would say it's quite straightforward, it's kind of boring. We just open a cursor, and then we, give me the data between X and Y, and that's it. Nothing fancy there. For the live streaming, we leverage one technology, which is called Postgres Notified Listen. So it's kind of like an internal PubSub build within Postgres. So we have a trigger whenever an event gets stored into this model events table. We will notify the event into the channel, and then the application code, the event string, will be listening for events from this channel. And basically, kind of like by pulling in a way, it will basically ensure that all the events are periodically sent to through the wire. And this is the events that basically we will get the events with a few milliseconds from being persisted. So the next part that I want to touch is a bit how do we scale this system? Because the thing about Revolut is scalability is quite critical. So this is basically the traffic pattern. Sorry, the event volume pattern of events being persistent by year. So as you can see, today we are with 108 billion records since the start of the year, and we already surpassed 2023. And I did a similar talk basically a month and a half ago, and we just persisted around, 30 billion records in pretty much like a month and a half. So basically this load keeps basically growing over time. So where I'm going is, keeping load under control is really important, because if you basically sit still and don't do changes to your system, eventually can hit you, and it will be quite problematic. So the first technology that we use is basically we leverage partitioning. So partitioning helps you to basically break down a table into smaller tables, and this basically has some advantages, no? So one of the advantages can be, for example, from inserts and read performance. Whenever you have a set of tables, Postgres has this concept of predicate post down, basically partition pruning. So only the table that you're actually performing, Postgres is able to know for a given record where the data is located, and based on that, it will be only issuing the query into that specific table. So for example, if we have a sample like that, where we have three tables under a parent table, and from the query perspective, we know that only the child B table contains the data, Postgres will only issue the query there. So basically you prevent eventual logs, and you prevent unnecessary scans over the table. So basically it gives you a performance boost, and also in terms of when you're inserting, it helps you to also basically reduce the planning time. And then finally, it kind of helps also in terms of maintenance operations. So in terms of partitioning, there is basically three types of partitioning. So there is the list partitioning, where you said, hey, this record, that record, or for example, we partition by country, and then you can have, one partition for Spain, one partition for Portugal, one partition for UK, for example. So other case can be by range, where you can set, values between X and Y are in a given partition, which, for example, in our case, we use it a lot to basically partition data in a temporal manner. And then finally, you can use hashing, which basically applies consistent hashing over the tables, and then you can decide basically how many buckets you have, and then basically you're able to distribute the load evenly. Finally, there is the concept of the default partition, which means if you define a partitioning strategy and there is some gaps of data, if you try to persist something outside that is not specifically configured, it will fall back into the default partition. So, it's kind of handy to catch errors, but yeah, it can bring some issues. So how do we scale? Historically, we started with a model like this. We used to have a table model events, and then in order to break down things, instead of having like a big table that contains all the events, we decided to basically break it down by using the range partitioning by months. So we were having, between the first of the given month and the 31st, we were persisting in this partition, the next partition, and so on. So this was giving us, for example, advantages that every single partition that you start, it contains its own set of indexes. It doesn't contain any sort of bloating, but it has kind of like one problem. You are only persisted in a single table. So despite which you have three tables available in this example, you will be only persisted in whichever is right now. I mean, the rest of the tables won't be actively inserted. So this small fire that I added is kind of meant to be kind of like a hotspot. So we got performance issues at some point, and then we basically did the straightforward thing. Instead of basically reinventing the wheel, we basically cut it down by weekly. So it gave us some basically bias down. We were basically not solving the problem, but it helped us to basically think in something more like a future-proof. But still, the problem was still there, and this traffic pattern the volume pattern that I was showing you before was the same. So basically, a few months after, we basically were in the same state. We were having problems because we were having this small partition. So for that, we leveraged another type of partitioning that I was discussing before, which is we started partitioning by list. So in our event store, we distribute the data. I mean, something that I didn't mention, but we distribute the data by domains. In event store, we call it modules. So what we ended up doing is, instead of having all the events into a single table, we create one partition for example, for core layer, which is our layer system, another one for identity, and few others. So basically, every domain will have a dedicated table, and then below the table, we will keep the same weekly partitioning strategy. So by doing this, we get one advantage. Every module now is totally isolated from the other, and basically you increase the parallelization by ensuring that every module basically gets persisted individually. That worked well for some time, but eventually we hit into issues. So what was the problem? The problem is that most of the modules are kind of small, but we were having kind of large applications. For example, this core layer at some point was having almost like 30–40% of the load into this event store system. So in addition to have the list partitioning that I was showing you, we added different buckets, hash buckets below. So basically that ensures that for every module now you have 5 buckets of parallelization. And you can basically change the number of buckets based on configuration, but you need to be careful. It's kind of like indexing. If you go too hard, eventually you get penalty because of it. So the advantage of this bucket is that you get an increased number of insertion throughput, but then you pay the penalty when you're reading it, in case you execute the query without providing the partitioning key. And then finally, we did something else, which was we removed basically the root of the problem. Originally, we were having these model events as an actual table. Then we decided to basically make these tables standalone tables. So basically, by that, we remove any sort of contention during insertions and operations, but it brings other set of problems. Now, each table is different, but from the application point of view, in reality, all these dynamic tables are the same table. So for example, if you want to execute maintenance, for example, adding a new column, now you don't add a column in a single table, you need to add a column in hundreds of tables across the system, so there is still some complexity. And then to finish, the second thing that we did is, the moment that we kind of optimize the performance within a single application, is we needed to thought into sharding. So we basically hit all the potential limits into a single database cluster. So first, we extracted all the historical data. So we created what we call the archive DBs. So the current clusters, the hot shards, basically only contains data which is basically the last couple of weeks. We're talking about 5 terabytes, 7 terabytes more or less for the hot DBs. And then the rest of the DB we flooded to these archive clusters. And in terms of sharding, of course, eventually we will always move to distribute further. So we started extracting shards basically by domain. So different departments have different dedicated shards for it. And lastly, we also started to do sharding in a regional manner. So for example, now we're extracting, for example, all the Mexican customers are in the dedicated shard, and we're doing the same for Europe, Brazil, Singapore, and so on. So basically, each region, if you think from the previous topology, you will have regional deployment, and then we will have all the other topologies that I was mentioning before. So in terms of the actual topology that we have, this is pretty much what we have at this point. We have the main DB events, the global one, where we have the modular DBs, and then we have a bunch of archives that contains all the historical data. And then we deploy gradually with the different regions that we're going to be added over time. So yeah, so this is it, guys. Thank you for your time. So as I mentioned, I briefly touched the Alpha, our CQRS framework. Then I describe how event store works under the hood, publisher, and focusing on the event streaming. And finally, we cover, how do we apply sharding and partitioning in order to scale our system. So yeah, if you folks have any questions, I will be happy to answer them.